In this video, we will talk about additional ways to synthesize amines and some reactions that amines undergo. Specifically, we'll talk about the alkylation of amines, alkylation of azide, the Gabriel synthesis, and reductive amination, and these are all synthesis reactions. Then we'll talk about nitrous acid reactions, specifically for aromatics, and the Hofmann elimination reaction. So one way to synthesize amines is to use alkylations. Now this type of reaction will involve nucleophilic substitution, and in these reactions, nitrogen will always be the nucleophile. So the way I like to remember it is nitrogen, because it has an N, means it's going to be a nucleophile. So just like nitrogens are considered weak bases, they're also considered nucleophiles. So in this reaction, we can take an amine, such as ammonia, and put it in the presence of an alkyl halide. Now this is an SN2 mechanism that we've seen many times before, but we're going to have the nitrogen act as the nucleophile, attack the carbon containing the leaving group, and kick off the leaving group. We form an intermediate with charges, and then in the presence of a base, which ammonia is, another ammonia molecule can remove the extra H from the N, restore it to neutral to form a primary amine. Now the problem with this reaction is you're capable of having multiple alkylations occur, so it's not easy to control the types of products you can get. So for instance, if we have ammonia in the presence of ethyl bromide, again our ammonia can act as a nucleophile because it contains a nitrogen. Now we will add an ethyl group to our nitrogen, then we can have another ammonia, remove the extra H. Now at this point we have a primary amine, but a primary amine still contains a nitrogen with lone pairs. A nitrogen with lone pairs is also capable of acting as a nucleophile. So if we have more of the ethyl bromide, we can have another nucleophilic attack occur. And again, once we remove the extra H, we'll end up forming a secondary amine. So this can continue. So at the end of this reaction, we could end up with several different types of products. We could end up with a primary amine. We could end up with a secondary amine. If it were to continue and this nitrogen were to act as a nucleophile, we could also end up with a tertiary amine. So this type of reaction is not very efficient because it's not easy to control what type of product you're going to end up with. So an alternative to the alkylation of amines is the alkylation of azide. In this reaction, we're using azide, which has this structure. It's 3 nitrogens, double bonded together. We've got 3 formal charges, and overall it has a minus charge. Now azide is a much better nucleophile than ammonia or any other type of regular amine. So now when azide comes in contact with an alkyl halide, such as again ethyl bromide, we can again have the same SN2 reaction occur. This will generate this intermediate, where we've now formed a bond between the end nitrogen and the 2 carbons. Now for the second step of the reaction, and this is a completely separate step, we're going to treat this molecule with LAH, and we're going to perform a reduction. In the end, we will generate a primary amine connected to 2 carbons, as well as nitrogen gas. Now, because this is a two-step reaction, this is step 1, this is step 2, we stop at this point in the reaction, and this is our final product. So we have no more of the alkyl halide that this primary amine can react with. Another way to make primary amines is the Gabriel synthesis. So again, this is specifically for making primary amines, and similar to the alkylation of azide, it avoids multiple alkylations. Now this reaction involves taking phthalimide, treating it with a base, following it up with an alkyl halide, and then finishing with hydrazine. Ultimately, we will generate a primary amine. So let's go ahead and take a look at the mechanism for the Gabriel synthesis. So we're starting off with the potassium hydroxide. Now the H attached to the nitrogen is very acidic, so the hydroxide will go and take that acidic H and give the electrons to nitrogen. Now the conjugate base that we generate is resonance stabilized, which is partly what makes this H so acidic. But now we have lone pairs on nitrogen that we know are capable of acting as nucleophiles. So in our next step with the alkyl halide, the nitrogen will act as the nucleophile, attack the carbon containing the leaving group, and kick off the leaving group. Again, this is an SN2 mechanism. So now the hydrazine comes in. With hydrazine, we have two NH2s connected to one another. Now again, the nitrogen is going to act as a nucleophile. It's going to come in and attack one of the carbonyl carbons and kick the electrons up onto the oxygen. In the next step, the electrons are going to come down, and we're going to break the bond between the carbonyl carbon and the nitrogen containing the R group. At this point, we will have a couple of proton transfers, which I won't show, which will involve removing the extra H from this nitrogen and protonating this one. Then the whole process is going to repeat itself. This nitrogen will act as the nucleophile and attack this carbonyl. Ultimately, when we're done, we're going to release the nitrogen and the R group, and the nitrogen will have two H's attached. And we will get the final primary amine. So the mechanism is just to give you a sense of how this reaction works. It's not something you'll be expected to show on the final exam. And the last reaction we're going to learn for synthesizing amines is called reductive amination. This type of reaction is a specific targeted type of alkylation where we start with an aldehyde or ketone, treat it with an amine, and it's a two-step reaction where we have an acid catalyst followed by a reducing agent. And this reaction can produce a primary, secondary, or tertiary amine depending on what we start with. So for example, if we start with an aldehyde and a primary amine, we treat it with an acid catalyst. Now we've seen this reaction before in the imine formation. So we form this imine here. Now with an imine, we have a double bond between the nitrogen and the carbon. So next, treating it with the reducing agent, we're going to reduce this double bond and replace it with hydrogens. So now we have a nitrogen bound to its original R group and now bound to a new carbon or R group. So we started with the primary amine and we created a secondary amine. So depending on the type of amine you start with, that's going to predict the product that can form. So for instance, if we start with ammonia and treating it with our aldehyde in the presence of an acid catalyst, again we're going to form an imine. Then reducing this, we're going to end up with a primary amine. So ultimately, our ammonia is generating the primary amine. We're going to constantly add one R group to our nitrogen. We can also start with a secondary amine. Now we learned in a previous chapter that a secondary amine plus an aldehyde or ketone in the presence of an acid catalyst will form an enamine. Now an enamine still contains a double bond, so once we treat it with the reducing agent, we're going to get rid of that double bond and replace it with hydrogens. But again, starting with the secondary amine, we can generate a tertiary amine. So we can control the type of amine that forms by using a specific type of amine as a reactant. So we are only going to go over two of the reactions of amines. We'll talk about the nitrous acid reactions as well as the Hofmann elimination. So with nitrous acid has the abbreviation HONO, and it is an aqueous solution. Now, nitrous acid is weak and it's an unstable acid. Because it's so unstable, you actually just can't buy bottles of nitrous acid. You have to prepare it in the reaction mixture. So we call that being prepared in situ. So in situ means prepared in the reaction. Now, the nitrous acid will react with all classes of amines, but it is most useful for aryl amines such as aniline. Now, nitrous acid is prepared from sodium nitrite and a strong acid such as hydrochloric acid. These together will produce our nitrous acid as well as a salt, which will still be dissolved in the solution. Now, once this is prepared in the reaction mixture, when it's in the presence of aniline or an aromatic attached to an NH2, these two will react to create a ring that contains an N triple bond N. Now this is going to have a positive formal charge. The chlorine will have a negative formal charge, which will stabilize it. Now this is known as a diazonium salt. And this is really important because the NN group is capable of being replaced by several other types of functional groups. Now we're not going to go over the mechanism for forming the diazonium salts, but just to give you a sense of the types of reactions that they can undergo, we'll look at here. So again, starting with a molecule such as aniline and treating it with sodium nitrite and hydrochloric acid will form our diazonium compound. Now again, this NN group can be replaced by a number of different functional groups. Now this group of reactions are known as the Sandmeyer reactions, and they are all copper-based. So if we treat this molecule with copper chloride, we'll replace the NN group with a chlorine. Copper iodide attaches an iodine. Copper cyanide attaches a cyano group. So these are alternative ways to add these groups to benzene rings. Similarly, copper bromide will attach a bromine. Other types of reactions, we can take this molecule and add a fluorine using HbF4. We can add an OH group or make a phenol functional group by using water and heat. We can use H3PO2 to completely get rid of the N2 group altogether and replace it with an H. This is a process known as deamination, and it's a way of getting rid of an amine group from a benzene ring. So again, these are just additional reactions that can be used when we're making derivatives of benzene rings. So the last reaction that we'll talk about with amines is the Hofmann elimination. And this reaction is specific for making alkenes that are the least substituted. So we talked about Hofmann products in Chem 226 that form the least substituted alkenes. Now this reaction involves taking an amine, treating it with excess alkyl halide, followed by silver oxide with water and heat. So this is a two-step reaction. We'll go ahead and take a look at the mechanism and reaction for step 1. So starting off, we have an amine. An amine itself is a bad leaving group because it's a strong base. So what we're going to do is we're going to take excess alkyl halide, such as methyl iodide, and we'll do multiple alkylations. Similar to what we saw in the very first reaction of this video. After all of the alkylations, we will end up with a nitrogen that has 3 methyl groups attached, as well as a positive charge. Now we've turned it into a great leaving group. And this charge will be stabilized by the iodide ion. In step 2, we take our amine with the good leaving group and the silver oxide with the water and heat will provide a hydroxide ion that's going to replace the iodide ion. So now we have a hydroxide that's a much better base than an iodide ion. So at this point, we will have an E2 reaction occur. Now the hydroxide is going to take the H on the least substituted carbon, and that's due to steric hindrance. Then the electrons will go and form the double bond and kick off the leaving group in an E2 mechanism. So the Hofmann elimination will always give the least substituted product due to steric hindrance, and this is going to be our final product.